Hey everyone, Mr. Boltri bringing you video 1.2 of AP Physics. Today we're going to be doing another lab. It's going to be the marble lab. So very much like the buggy lab, the purpose of the marble lab is going to be to investigate the relationship between the position and time for a given object. This time the object we're going to be investigating is a marble rolling down an inclined ramp. So my setup is pretty straightforward. We just have an inclined ramp and a marble, which we're going to roll down the ramp. And before we start, let's set up the data table. Like I said, we're going to be grabbing the position at a bunch of different times. So at 0 seconds, 1 second, 2 seconds, and we're going to grab a bunch of different positions at those times. So running the actual lab, we just kind of put the marble at the top of the ramp. I moved my finger out of the way so as not to give it a push either up or down. And then the marble rolls down the ramp. We recorded it with a video, so then we can slow down that video and grab the position at a bunch of different timestamps on the video. But before I move on, I want to watch the video again, just to look at what's happening with the velocity of the ball as it's rolling down the ramp. So at the beginning, I move my finger so as not to give it a velocity. So it moves slow at the beginning, and then as balls typically do as they roll down ramps, it speeds up and gets faster and faster and faster. So we have our position versus time data, and at this point, hopefully when you see a data table like this, your first instinct is to graph it, which we can do, and we can see that the position versus time data for this marble looks something like this. And I hope that you can agree with me when I say I think it's this linear line of best fit. If we try to do a line of best fit, it does not approximate the data very well. And the reason that is because the data seems to have a clear curve to it, that if we try to do a linear fit to our data, it misrepresents the data. So instead, we can try to do a different kind of fit to match our nonlinear data. I tried a quadratic fit, and it seems to represent the data a lot better. So we definitely have some sort of curvy data. And then the question becomes, how can I translate from a curvy position versus time graph, a nonlinear position versus time graph, and make a velocity versus time and an acceleration versus time graph based on that? Because the AP exam really likes for you to be able to translate between the different kinds of graphs. So first, let's focus on moving from the position versus time graph, the nonlinear position versus time graph, and making a velocity versus time graph based on that. But before we get started, I do need to take a little break to talk about the vocabulary related to velocity. So there's kind of two different flavors, two different types of velocity. There's the instantaneous velocity, which is the velocity at a given moment, a given instant, a clock reading, if you will. And then there's the average velocity, which is over a time interval. You take all the different instantaneous velocities and you average them together. You may be moving fast and then slow, and those kind of average out to be kind of a medium average velocity. So instead of talking about it theoretically, I want to use the specific example of the marble data. So first, let's look at what does average velocity look like on a graph. So if I want the average velocity between 0 seconds and 5 seconds, I know that the slope of a position versus time graph is still the velocity. But which flavor of velocity, instantaneous or average, do I get when I find the slope between 0 seconds and 5 seconds? You can think about it like this. Basically, that's the equivalent of saying, well, the only two pieces of information I know is where the object started and where the object ended. And I know that it took the object 5 seconds to go from point A to point B. So if I know that it took the object 5 seconds to go 110 centimeters, I can say that the average velocity of the object is 22 centimeters per second. And so the object may have been moving at a constant velocity of 22 centimeters per second. It may have been going slow at the beginning and fast at the end, but all I know, knowing point A and point B, I can find rise over run, which is change in position over change in time, and that'll give me the average velocity only knowing the starting and ending points, which actually explains where the definition for the equation for average velocity comes from. So that V with a line above it is also called V bar, and the bar represents average. So that's average velocity equals change in position divided by change in time, which is position final minus position initial divided by change in time. It's basically rise over run for the secant line that we showed in the last slide. It's basically rise over run for this section of the graph. So that's a secant line because it goes through 2 points on the graph. It goes through the graph here and here. So then the other thing I want to think about is how do we find instantaneous velocity by looking at the position versus time graph? Because slope of a position versus time graph is still velocity. But now we don't want the slope from point A to point B. We just want the slope at a specific instant, at a specific moment in time. But the slope is always changing because of the curve that we can see here. So hopefully I'm going to reintroduce you to a concept of a tangent line. And a tangent line touches the function only once on the outside edge. So you can see here the tangent line at 0 seconds is this blue line. And I have animated the graph to show the tangent line every half a second. So you can see the tangent line at 2, at 3, at 4, and at 5 seconds. You can see that the slope gets steeper and steeper and steeper of the tangent line, which makes sense because as the ball or the marble was rolling down the ramp, it was getting faster and faster and faster. So we can freeze frame right here and try to figure out the slope of the tangent line at 2 seconds. If we find the slope of the tangent line at 2 seconds, then that gives us the instantaneous velocity right there at 2 seconds. So then what we can do is we can go in and draw a bunch of tangent lines every second or every half second and find the slope of all those tangent lines, which will give us a bunch of instantaneous velocities. Now, this is a long and tedious way to do it because we have to draw a bunch of tangent lines. And it's not the most accurate because we might be able to mess up the drawing of our tangent line. A much quicker and more accurate way to do it is using calculus, which I am so excited to teach you in next lesson or the lesson after that. But before I dive straight into the calculus, I wanted to make sure that you understood the basic premise of using the slope of the tangent line to find the instantaneous velocity, which is the instantaneous rate of change in position with respect to time. So like I said, draw a bunch of tangent lines, find the slope of those tangent lines, and then you'll have a bunch of instantaneous velocities. And really, I should write instantaneous velocity right here just to be clear that we're talking about instantaneous velocity. Once you have those instantaneous velocities, you can graph it, and we get a pretty linear graph, which makes sense because as time is increasing, the velocity is getting bigger and bigger and bigger. And that's all that this graph shows. But it's exciting that we get a linear velocity versus time graph because then we can draw a line of best fit. And we remember the slope of a line of best fit on a velocity versus time graph is change in the velocity with respect to time, which we call acceleration. So when we find the slope of this VT graph, we see that the acceleration of the marble rolling down the ramp is 8.7 centimeters per second each second, or 8.7 centimeters per second squared, which means that every second that goes by, the marble moves 8.7 centimeters per second faster than it did the second before. So now that we have the position versus time graph and we figured out how to translate the position versus time graph, the curvy or nonlinear position versus time graph into a linear velocity versus time graph, the question becomes, how do we figure out the acceleration versus time graph? So again, looking at the slope of the velocity versus time graph, the slope is 8.7 centimeters per second squared, and it is a constant slope. So we can say the acceleration has a constant acceleration of 8.7 centimeters per second each second for the whole time. And now that we have this AT graph, acceleration versus time graph, we can start to analyze it. So the vertical intercept is not often very interesting, and in this situation, it's not very interesting. It's just the initial acceleration. It's also the only acceleration because it had a constant acceleration, but in future examples, we are going to be having a changing acceleration, so things are going to get a little bit more interesting. And when we do have a changing acceleration, then we might want to look at the slope, which is the rate of change in acceleration with respect to time. The fancy vocabulary word for the rate of change of the acceleration with respect to time is called jerk, or sometimes jolt. But you don't need to know either of those two words for the AP exam. If they ever want you to find the slope of an AT graph, they will ask you, what is the rate of change in acceleration with respect to time? They're not ever going to say, what is the jerk? But doing rise over run, we can see that the units of the jerk are centimeters per second squared each second, which is a change in acceleration divided by a change in time, or centimeters per second cubed, which is just easier to say and to write. And just like in the last video, I would ask that you find the meaning of the area of an acceleration versus time graph by investigating what is the actual value and what are the units. So that brings us to the end of video 1.2, the end of the Marble Lab, which was introducing you to an example where an object was experiencing a constant acceleration. In future examples, when objects have non-constant or changing accelerations, then we're going to have to start using even more interesting tools like calculus. But I just wanted to establish a strong foundation where you could understand a pretty simple example of an object moving with a constant acceleration to see what that does to how the velocity changes and what that does to what the position versus time graph looks like and how the position changes with respect to time. So looking forward to exploring calculus in the future, but for now, hope you enjoyed the Marbles Lab. This is Mr. Boltri signing off, and go Bears.